oyster shells into Charlotte Harbor today to help boost water quality and help our fish and anglers. The shells act as a natural filter to get toxins out of the ecosystem.
There is a stretch of the Gulf of Mexico off the coast of Cedar Key, Florida, where the seafloor used to be nothing. Not nothing in the poetic sense. Nothing in the biological sense. Flat, featureless sand, swept clean by currents, offering no grip, no shelter, no reason for anything to stay. Fishermen who had worked those waters for decades knew it as dead ground. Scientists who studied it called it degraded substrate. Everyone who looked at it agreed on one thing. It was not coming back on its own. Then, between 2007 and 2024, the Florida Fish and Wildlife Conservation Commission made a decision that looked, from the outside, like organized recklessness. They collected more than 500,000 tons of discarded oyster shells from restaurants, seafood processing facilities, and commercial kitchens across the state. They loaded those shells onto barges, and they dumped them into the Gulf. No precision engineering. No synthetic reef structures. No carefully designed marine architecture. Just the accumulated leftovers of countless seafood meals, hauled out to open water and dropped into the deep. The backlash was immediate. Environmental advocates called it industrial ocean dumping wrapped in conservation language. Commercial fishermen who had spent generations reading those waters warned that the shell deposits would smother whatever fragile organisms still clung to life on the soft bottom, disrupt the current patterns their livelihoods depended on, and permanently alter fishing grounds that had fed their families for a century. The critics were not fringe voices. They were experienced, credible people with legitimate reasons for concern. Even the scientists who designed and managed the program were not optimistic about timelines. Artificial reef projects, when they work at all, typically require years before biological response becomes measurable. The researchers who oversaw the Cedar Key depositions built their projections around conservative assumptions. They expected slow, modest results at best. They braced for failure at worst. What actually happened on that Gulf seafloor was something that none of them had modeled, predicted, or fully prepared for. Within months, not years, life was colonizing the shell mounds at rates that had no parallel in existing scientific literature. A system that had been biologically dead was transforming into something complex, layered, and self-sustaining faster than the tools available to measure it could keep pace. And the story of how that transformation happened, the actual mechanics of what occurred on that silent seafloor, reshapes fundamental assumptions about ecological recovery, coastal engineering, and what discarded waste is actually capable of becoming. To understand why Florida's Gulf Coast needed intervention at all, you have to understand what was lost before the program began. Oyster reefs once dominated Florida's coastal shallows in a way that modern residents of those communities would find almost unrecognizable. Stretching across hundreds of square miles of nearshore Gulf habitat, these reefs were not simply piles of shells. They were living infrastructure, biological engines that filtered enormous volumes of seawater daily, stabilized coastlines against storm surge and erosion, and provided structural habitat that supported an estimated 300 or more distinct marine species. The reefs were the organizing architecture of the entire coastal ecosystem. Everything else, the fish populations, the seagrass beds, the water clarity, the shoreline stability, was downstream of the reefs. That infrastructure was dismantled over roughly a century. Commercial overharvesting in the late 19th and early 20th centuries stripped reefs that had accumulated over thousands of years of biological activity. Coastal development altered water flow patterns and introduced chronic pollution loads that made reef recovery difficult, even where harvesting pressure was reduced. Agricultural and urban runoff poured nitrogen and phosphorus into coastal waters at rates the remaining oyster populations could not process, fueling algal blooms that clouded the water and suffocated bottom-dwelling organisms. Warming water temperatures added additional physiological stress. By the early 2000s, Florida's Gulf Coast oyster reef network had been reduced to a fraction of its historical extent. In many areas, it was functionally gone. The ecological consequences were cascading and compounding. Without hard substrate, oyster larvae drifting in Gulf currents had nowhere to land and survive. Without larvae settling and growing, no new reefs formed. Without reefs filtering water, clarity declined further. Without water clarity, seagrass beds contracted. Without seagrass, juvenile fish lost critical nursery habitat. The system was locked in a downward spiral with no internal mechanism capable of reversing it. This was the situation the Florida Fish and Wildlife Conservation Commission was confronting when they began designing the shell deposition program. The logic of using recycled oyster shells was both practical and ecological. The shells were going to landfills anyway, representing a disposal cost and a wasted material. If they could function as reef substrate, the program would simultaneously solve a waste management problem and address a conservation crisis. The approach was inexpensive compared to conventional artificial reef construction using concrete or steel. And oyster shells, composed primarily of calcium carbonate, were chemically and structurally identical to the natural substrate that had been stripped from those coastal waters over decades of exploitation. The question was not whether the concept was sound in theory. The question was whether it would actually work in practice, and if so, how long it would take. The first monitoring surveys after the initial depositions returned data that scientists on the program were not expecting to see so quickly. The timeline for biological response on an artificial reef, under normal conditions, runs roughly 2 to 3 years before any significant colonization becomes detectable. Early surveys of the Cedar Key shell deposits, conducted at the 18-month mark, should have shown at most the earliest traces of microbial activity and perhaps scattered barnacle attachment. What they found instead required multiple rounds of verification before the team felt confident reporting it. Life had not merely appeared on the shell surfaces. It had organized itself into a functioning microscopic ecosystem that, by every measurable parameter, was further along than any comparable artificial reef project at the same elapsed time. The explanation for that speed begins with something almost impossibly small. Within days of the shells contacting the seafloor, bacteria began colonizing the calcium carbonate surfaces. These were not random, passive settlements of opportunistic microbes. They were structured communities, forming organized biofilms, thin but architecturally complex biological carpets that effectively converted dead shell surfaces into functional microhabitat. The biofilms created temperature gradients, chemical gradients, and physical textures that made the shells hospitable to the next wave of organisms in ways that bare calcium carbonate simply could not support on its own. Simultaneously, the shells themselves were doing something chemically significant. Oyster shells are composed predominantly of aragonite, a crystalline form of calcium carbonate that dissolves gradually in seawater. As those shells released calcium ions into the surrounding water, they created localized zones of elevated alkalinity immediately adjacent to their surfaces. Those chemical microenvironments were precisely the conditions that calcifying organisms, barnacles, tube worms, juvenile oysters, require to attach, build their own shells, and survive. The deposited shells were not merely providing surface area. They were chemically engineering the local water chemistry to facilitate their own colonization. The process was almost paradoxically self-activating. Within weeks, diatoms and filamentous microalgae moved into the established biofilms, layering atop the bacterial communities and building the base of a rudimentary food web. Microscopic crustaceans and larval mollusks followed, grazing the algae and bacteria. Their presence drew the first juvenile fish, which arrived to feed on the grazers. Each successive layer of biological complexity fed and enabled the next. The process was not directed by any external force. It was a cascade, each stage creating the conditions that made the following stage possible, running itself in a self-reinforcing loop. This invisible phase, the bacterial colonization, the biofilm formation, the chemical alteration of the water, was the hidden foundation on which everything visible later was built. And it was happening on a timescale that had never been documented on any comparable substrate in the scientific literature covering Gulf Coast marine ecology. The significance becomes clear when you compare it to what a sandy seafloor can and cannot do. Sand offers no attachment surface for calcifying organisms. It provides no chemical microenvironments. It holds no structural complexity that could shelter microscopic life through current fluctuations or temperature changes. The soft-bottom Gulf floor that characterized the Cedar Key sites before the deposition program was biologically constrained at the most fundamental level. Not because the water lacked the right organisms, but because the substrate offered nothing those organisms could use to establish themselves. The shells bypassed that constraint entirely. They introduced surface, chemistry, and complexity all at once, and the biology of the Gulf simply filled the opportunity as fast as the physics allowed. The next chapter of the transformation involved constraint that had been quietly strangling oyster populations along Florida's Gulf Coast for decades before the program began. Oyster larvae, called spat, are planktonic. They drift in currents, carried wherever the water moves, and when they are developmentally ready to settle, they search for hard substrate on which to attach and complete their metamorphosis into juvenile oysters. The problem, going back to the extensive destruction of Florida's natural reefs, with that hard substrate in the Gulf's nearshore zones had become vanishingly rare. Spat were being produced. The remaining adult oyster populations were still spawning, but the larvae were drifting through open water with nowhere suitable to land. Without substrate, they could not settle. Without settlement, they died. A generation of oysters was being lost continuously, not because of continued direct harvesting, but because the physical infrastructure their survival depended on no longer existed. The population had no mechanism for self-renewal. The deposited shells resolved this bottleneck with remarkable directness. Each shell pile was, from the perspective of drifting spat, a concentrated landing zone. The irregular surfaces of stacked and interlocked shells offered attachment points in enormous numbers. The localized chemical conditions created by dissolving aragonite were hospitable to the calcification processes juvenile oysters need to begin forming their own shells. And the shell deposits had been positioned at sites along Gulf current pathways that carried spat naturally across those locations. The first generation of juveniles settling on the deposited shells was documented within the first year. Numbers significantly exceeded the projections that program scientists had developed based on comparable reef restoration projects elsewhere. The larvae were not just finding the substrate. They were thriving on it at densities that suggested the Gulf's reproductive capacity had been constrained by substrate availability far more severely than previous modeling had estimated. By the second year, those first-generation juveniles had grown to reproductive maturity. They were spawning, releasing their own larvae into the current, larvae that settled on the existing reef structure and added a second biological generation to the accumulating mass of shells. The program had created the initial physical conditions. The oysters were managing everything else. Each generation that matured and died contributed its own shell to the substrate, building the reef upward and outward without any additional human input. The structure was growing itself. By the third year of monitoring at established sites, survey data recorded oyster densities approaching 850 individuals per cubic meter of deposited shell material. Equivalent areas of soft bottom habitat nearby, with no substrate, supported effectively zero. The biological difference between a patchy pile of water-discarded restaurant shells and a featureless stretch of Gulf sand was not incremental. It's categorical. The reef sites had become a different ecological world entirely. Fish followed structural complexity onto those reefs with the predictability of a physical law. The moment three-dimensional habitat appeared on the featureless Gulf bottom, species that require that complexity for feeding, shelter, and reproduction began arriving and staying. Survey data from Cedar Key reef sites documented biomass increases exceeding 340% relative to control areas of unmodified soft bottom. Species diversity increased by approximately 280%. What made those numbers scientifically significant, rather than simply impressive, was the careful distinction researchers drew between fish aggregation and fish production. Artificial reefs made of concrete, sunken vessels, or prefabricated reef modules have a well-documented tendency to concentrate fish populations that already exist in the surrounding area. The fish move from elsewhere to take advantage of new structure. Survey counts around the new reef look dramatically elevated, but total population has not increased. The fish are redistributed, not multiplied. The Cedar Key data told a different story. Juvenile fish counts, animals spawned in those waters and surviving to maturity within the reef system, were driving the biomass increases. The reefs were producing fish by creating habitat conditions that supported survival through the most vulnerable life stages. The juvenile phases, when shelter from predation and access to food are the determining factors in whether an individual survives. Red drum, sheep's head, flounder, snook, and numerous other commercially and recreationally significant species were completing their life cycles in habitat that had not previously supported them. The reversal in public perception that accompanied this biological transformation was arguably as significant as the ecological data in determining the program's ultimate trajectory. Charter fishing operators who had testified against the program, who had argued vigorously at public hearings that the shell deposits would destroy their livelihoods, found themselves filing formal requests to the same commission they had fought 6 years earlier, asking for new reef sites near their most productive fishing grounds. The shift was not gradual. It was emphatic. Fishermen who spent their working lives reading the behavior of fish in those specific waters saw the change immediately and understood its implications before the scientific surveys had finished processing the numbers. The economic consequences extended well beyond the charter fishing sector. Hotels, waterfront restaurants, bait shops, and other businesses tied to recreational marine activity around Cedar Key reported measurable revenue increases they attributed directly to the marine recovery around the reef sites. The ecological restoration had generated an economic restoration simultaneously, and it had done so without any subsidy, any management intervention, or any mechanism other than oysters doing what oysters have always done when given suitable conditions. One adult oyster filters between 30 and 50 gallons of seawater every single day. That figure, unremarkable in isolation, becomes extraordinary at reef scale. Hundreds of thousands of oysters thriving across the Cedar Key reef sites were collectively processing billions of gallons of Gulf water daily, extracting suspended particles, excess nutrients from agricultural and urban runoff, harmful bacteria, and the algae fueling nitrogen and phosphorus compounds that have been driving the degradation of Gulf coastal waters for decades. No machinery, no energy input, no maintenance cost. A biological filtration system of industrial scale operating continuously on its own metabolic processes. The ecological significance of that filtration capacity was visible in the water. Clarity around the reef sites improved measurably within a few years of reef establishment. Dissolved oxygen concentrations rose. Harmful algal bloom frequency declined in waters near active reef sites compared to surrounding areas. The improvements were not staying contained to the immediate reef zones. They were radiating outward, affecting water quality across a growing radius as the reef systems expanded and matured. Clearer water created conditions for a second cascade of ecological recovery that researchers had not initially projected as a primary program outcome. Seagrass, the submerged flowering plants that form some of the most productive marine habitats in the Gulf, require light penetration to photosynthesize and survive. Decades of declining water clarity had contracted seagrass beds across Florida's Gulf Coast, cutting off habitat that juvenile fish, manatees, sea turtles, and numerous invertebrate species depend on. As oyster filtration improved water clarity around the reef sites, sunlight began penetrating to depths that had been too turbid for seagrass growth. Seagrass beds began expanding into those zones. And as they expanded, their root systems and leaf structures stabilized bottom sediments, which reduced suspended particles in the water, which improved clarity further, which enabled more seagrass expansion. A second self-reinforcing positive feedback loop had been triggered by the first, with benefits compounding and spreading across the broader coastal system in ways that extended far beyond the reef footprint. The program had been designed to restore oyster reef habitat. It had accidentally initiated an interconnected restoration of the entire coastal ecosystem that those reefs anchored. Independent analyses of the ecological services generated by the 500,000 tons of deposited shells estimated the economic value of filtration services alone in the tens of millions of dollars, representing infrastructure costs that would have been required to replicate those functions mechanically. Nature was providing them at no ongoing cost and improving the delivery year over year as the reefs grew. The test that nobody had designed for the program arrived in September of 2017 in the form of Hurricane Irma. A Category 4 storm with sustained winds exceeding 150 miles per hour, Irma drove catastrophic storm surge and wave energy into Florida's Gulf Coast with a kind of force that routine coastal engineering. Oyster shell accumulations, both the living reef surfaces and the surrounding sediments they influence, sequester organic carbon, incorporating it into shell material and trapping it in the sediment column, where it does not contribute to atmospheric carbon dioxide concentrations or ocean acidification. Oyster reef restoration was beginning to appear in climate adaptation frameworks not simply as habitat recovery or coastal protection, but as a meaningful carbon management tool. The program had grown into a sea is designed to withstand but frequently fails to handle. Communities near Cedar Key prepared for the erosion, property damage, and infrastructure destruction that major Gulf hurricanes reliably deliver to exposed coastlines. Post-storm damage assessment data produced results that significantly altered how coastal engineers and state resource managers thought about the program. Shorelines backed by the restored oyster reef systems had experienced dramatically less erosion than adjacent unprotected stretches of coast exposed to equivalent storm energy. The reduction in erosion at protected sites averaged between 30 and 40% compared to unprotected areas experiencing the same storm conditions. The mechanism was structural. Oyster reefs do not present a smooth surface to incoming wave energy. They are architecturally complex, irregular, and three-dimensional in a way that engineered hard structures generally are not. Dense clusters of living oysters stacked on layers of accumulated dead shell, interlocked and rough-surfaced, absorb and dissipate wave energy through friction and turbulence rather than deflecting it. Waves approaching a reef system lose height and force progressively as they interact with that complexity, arriving at the shoreline behind the reef significantly weakened compared to their open water energy levels. Engineering estimates attributed approximately $3 million in prevented coastal property damage to reef protection during Irma alone. The total expenditure of the entire 15-year shell deposition program across all Cedar Key sites was approximately $5 million. A single storm had nearly returned the full cost of the program in damage avoided, and the comparison became even more compelling when examined over a longer time horizon. Conventional hard coastal engineering structures, seawalls, riprap, concrete barriers, are expensive to install, require periodic maintenance, and degrade under repeated storm loading. Each major storm cycle leaves them structurally weaker than the previous cycle. The oyster reefs demonstrated the opposite response. Storm damage, far from weakening the reefs, triggered new larval settlement on exposed shell surfaces and stimulated the next generation of oyster growth. Each storm that impacted the reefs left them with additional structural complexity and greater biological density than before. The protective system was strengthening itself through the same events it was designed to protect against. The Irma data introduced a compelling economic and practical argument to a conversation that had, until that point, been driven primarily by ecological reasoning. Coastal managers who had never engaged with oyster restoration as a serious infrastructure option found themselves without a strong counterargument. A self-repairing, self-expanding coastal defense system that cost a fraction of conventional alternatives and improved its performance with age was not easy to dismiss on practical grounds. By the early 2020s, the oldest Cedar Key reef sites had expanded to roughly double their original deposited footprint without any additional shell input from the program. The expansion was driven entirely by the biological cycle of the reefs themselves. Each generation of oysters settled on existing structure, matured, spawned the next generation, and contributed its own shell to the accumulating substrate upon death. Vertical growth added height to the reef profiles. Horizontal spread extended the reef's footprint in every direction from the original mounds. The structure deposited by human hands in 2007 had become a self-architecting biological system following its own developmental logic. The structural complexity of the mature reefs bore little resemblance to the loose shell mounds of the early depositions. 15 years of biological accumulation had produced reef architecture that included vertical profiles, sheltered gaps between dense oyster clusters, overhangs, and interlocking surfaces, creating dozens of distinct microhabitats simultaneously usable by different species. Crabs occupied the complex crevices in the lower reef structure. Juvenile fish sheltered in the gaps between oyster clusters. Octopuses established territories in the reef's deeper recesses. Sea turtles foraged across the invertebrate communities, coating the hard surfaces. Dolphins worked the outer reef edges, systematically hunting the dense fish concentrations those structures supported. Biodiversity metrics at the most established sites were approaching levels documented at some of Florida's natural limestone reef systems that had developed over geological timescales. The trajectory being traced by the Cedar Key reefs suggested that given sufficient time and continued freedom from the pressures that destroyed the original reefs, the restored systems would eventually reach ecological equivalence with the natural reefs they had replaced. That outcome had been considered essentially impossible when the program launched. Emerging research at those mature sites was also documenting a function that had not been part of the original program rationale. Dense limit intervention almost entirely by accident. The global footprint of what began as a Florida waste disposal problem is now measurable on multiple continents. Alabama launched its own shell recycling reef program by 2015, following the emerging Cedar Key model. Mississippi and Louisiana initiated comparable efforts. The Billion Oyster Project in New York Harbor adopted the same fundamental principle in one of the most severely degraded urban waterways in North America. Coastal engineers and marine restoration scientists in Canada, Australia, and multiple European countries began actively studying the Florida experience, seeking to apply its lessons to comparable problems of degraded shorelines and lost oyster reef habitat in their own coastal zones. The conceptual framework emerging from those international exchanges had a name: circular environmental design. The principle is straightforward in retrospect, though it was not obvious when the Cedar Key program launched. Materials that the human economy has classified as waste, oyster shells, coral fragments, limestone rubble, certain categories of industrial byproduct, retain physical and chemical properties that can function as ecological infrastructure when reintroduced to the environments those materials originally came from. Rather than treating waste as an end-state problem to be managed through permanent removal, circular environmental design treats it as a misallocated resource whose redirection to appropriate ecological contexts can generate restoration outcomes at costs far below conventional approaches. Florida's program demonstrated that principle at scale across 15 years through multiple storm cycles under scientific monitoring that documented every stage of the transformation. The data set it produced was not a single promising result from a pilot trial. It was a longitudinal record of an ecosystem rebuilding itself from discarded restaurant waste, covering more than a decade and a half of continuous biological development and expansion. What happens on the Cedar Key seafloor today is the continuation of a process that was set in motion by a barge full of shells dumped into uncertain water in 2007. The program that deposited those shells is complete. The ecology it initiated is not. New oyster generations are settling on surfaces built by generations that came before. Juvenile fish are completing life cycles and habitat that did not exist 20 years ago. Water that flows across those reefs is measurably cleaner when it leaves than when it arrived. Shorelines behind the reef crests are measurably more stable than they were before the reefs existed. And the reef footprint is larger this season than it was last season, by the accumulated work of organisms following biological imperatives that have nothing to do with human conservation goals and everything to do with the opportunity that a pile of discarded shells happened to provide. The scientists who monitored those first 18-month surveys, bracing for failure and finding instead an ecological acceleration they could not fully explain, eventually reached a conclusion that the data forced on them rather than one they had anticipated. The intervention was not what had rebuilt the reef. The intervention had provided the initial conditions, the physical surface, and the chemical opportunity. Everything that followed was the Gulf of Mexico doing what it had always been capable of doing, given half a chance and a foundation to work with. 500,000 tons of oyster shells, written off as restaurant waste, tipped into the Gulf without certainty that anything useful would result. What formed down there was not a reef in the conventional sense. It was a demonstration, running in real time, of what biological systems are capable of when the one thing they were missing is restored to them. The lesson from Cedar Key is not simply that oyster restoration works. It is that the ocean, given a foundation, builds the rest. You just have to give it something to start with.